6.3b, we're going to compute and interpret probabilities involving normal distributions. So here we're going to roll some doubles. In many games involving dice, rolling doubles is desirable. Rolling doubles means the amount of two dice are the same, such as getting 1-1 or 5-5. The probability of rolling doubles when rolling two dice is 6 out of 36 or 1/6. Okay, X is going to be this event. The number of doubles in 4 rolls of two dice. Then X is binomial. If that's the case, what is N and P? N is the number of trials, so 4. P is the fixed probability of 1/6. Does this meet bins? Is it binary? Success or failure, you get doubles or don't get doubles. Is each roll independent? Yes. Is there a fixed number of trials? Yes, there's 4. Is there a probability is constant? Yes, 1/6. So bins works. So let's do this. To figure it out, what you can do is we want to find the probability, it says here, of X being 0, which means what's the probability that you don't get doubles? Well, you can think through that. The probability that you don't get doubles is that you're going to have 30 out of 36, or 5/6 of the time you don't get doubles. So that's in one roll. But I want to know, what about if you do it 4 times? So think about it. You roll once, 2, 3, 4 times. Let's roll 1 and 2 and 3 and 4. Remember, they're independent. If they're independent, you can multiply the 4 scenarios together. So the constant probability in here is going to be, I'm going to use 5/6. So what's the probability of not getting doubles in this scenario? To not get doubles 4 times would be the 5/6 to the 4th power. The answer here is 0.482. Okay, so we've got the first scenario that the event of no doubles is 0. Let's move on to the next. What if the probability of X is 1? What's the probability that I get doubles 1 time in my 4 trials? Well, there's 4 different ways for me to have success 1 time in 4 tries. Do you agree with this? If I write down the 4 different ways to get success and failure, I'm either going to succeed the first time and fail the next 3, or I succeed the second and fail the others, I succeed the third and fail the others, or I succeed the last time and fail the others. There's 4 ways for this probability to happen. So what I first need to do is think about, how does the first way work? Well, just think logically. Again, we have 4 independent rolls. If this scenario happens, what is the probability of success? That is, getting doubles. Well, the probability of getting doubles is 1/6, so that would be here. And then what's the probability of fail, fail, fail? Well, that's going to be 5/6. So if you look at it this way, we can actually do shorthand. That is, we could say each way is going to be 1/6 and then 5/6 3 times. But that just represents this first scenario. I have these others to account. So what should I do to this particular probability right here I just found? Well, I have to account for it 4 different times. So when you do that, you're going to actually times it by 4 and get this value right here as your probability. Well, what about the other scenarios? What's the probability of getting doubles in 4 rolls exactly twice, exactly 3 times, exactly 4 times? Well, I'm going to write out the probability of getting doubles exactly twice. In this case, there's going to be 6 scenarios of success and failure. I could have failure on the first 2 and success on the last 2 where I get doubles. Or it could be mixed around, the success is in the middle. If you look at it, there's going to be 6. Okay? What about a success 3 times exactly? Well, there's actually going to be fewer for this one. What if I have success 3 times and failure last? What if it's in this order, or this order? There's 4. In the last one, what's the probability of success of all 4s? There's only one outcome for this one, which is going to be 4 successes in a row. Now, if I was asked to compute this one, it's not going to be that difficult. What you're going to do is success in this case, remember, was 1/6, and I do it 4 times. It only happened once, so I don't have to multiply it by anything. So if I simplify this number, I will get the answer. Okay. What about the 3 trials? Well, think about these, 3 successes and a failure. Folks, 3 successes would be 1/6 3 times. The failure was 1 failure at 5/6, but I have 4 scenarios, so I should take this and times it by 4. Okay, what about working backwards here? 2 failures and 2 successes. Let's do the 2 successes is 1/6 of a time. There's 2 of those. Failures, 5/6 2 times. But in this case, we have 6 outcomes, so I times it by 6. The one thing you should notice is that in all of these examples, if you just look at this, there's 4 trials. Here's the 4 trials. Here's the 4 trials. You're basically distributing the outcome of the 4 trials amongst the probability of success and failure. Now, when we saw that some of the scenarios happen 4 times or 6 times or 1 times, what we were just looking at is called the binomial coefficient. And what it is, the number of ways an arrangement of success and failure in n observations can happen. And there's actually a thing in your calculator that will actually compute this for you. This is on the formula sheet. This is called the combination. And what it is n factorial divided by k factorial over n minus k factorial. This is what factorial means. It means multiply from that number all the way down to 1. Let me give you an example. When we were talking about rolling the dice 4 times, so we're going to do 4 trials, which is our n. Now, let's look at the event when I said k is 3, so I wanted doubles to happen 3 times. So I'm going to put 3 in here. Formula-wise, what I would do is just put 4 in for n, 3 in for k. So I would write it as 4 factorial over 3 factorial minus 4 minus 3 factorial. That's going to be 4 factorial on the top. Folks, 4 factorial means 4 times 3 times 2 times 1. 3 factorial means 3 times 2 times 1. Okay? 4 minus 3 is 1. 1 factorial is just 1. So if you look at this, what you're going to see is these actually cancel out, and what you're left with is they're going to tell you there's 4 combinations. So you can do this by hand, but I'm going to tell you, you will not have to do this by hand. In the calculator, what you can do is if you go to Math, scroll to Probability, you're going to look for this button called NCR. This is called a combination. How you would type this in the calculator is I'm going to mimic that I want to find that this would have been 4. You first type in 4, then you go find this in the calc, and it'll show NCR, and then you're going to type the 3. When you hit enter, it will tell you that there's 4 possible combinations. It's not necessary that you know this, but the binomial coefficient is actually related to Pascal's triangle. So if you're used to seeing this related to the polynomials and how the coefficients work on this would be a first degree, a second degree, a third degree polynomial, it is actually related to this. Don't worry about it though. Okay, here's the one formula I want to point out. This is on your formula sheet, and it's really quite handy. It is the formula to find the binomial probability given x equals a particular event. We're going to actually use this in our examples going forward. Let's go back to the rolling doubles, and we're going to do this using this new formula versus really thinking through it. So we're rolling the 2 dice, we're looking for doubles, probability of success is 1/6, right? So that's P. We're rolling the dice 4 times, so that is our N, our number of trials. They want us to find the probability the player gets doubles twice in 4 attempts. So I define X as the number of doubles. X has a binomial distribution. We've talked about the N and the P. I want to find the probability that X is exactly 2. So what I would do, here's how I would put that into the binomial formula. All I need to do, I have 4 trials, I want 2 successes. The probability of success is 1/6, and there's 2 successes that'll happen, which means the probability of failure is 5/6. To make up the 4, there has to be 2 failures in this one. Now this in your calculator is going to be the NCR, so what you would type for this one is 4 NCR2. When you do that typing, you actually get that at 6. Okay? So I'm going to do 6 times 1 6 squared, 5 6 squared, and I'm going to get the probability, which we could have gotten longhand. Okay, a third way to do this. You can think through it logically, like we did at the beginning. You can use this binomial formula, which I highly recommend. I like the calculator. In the calculator, you're going to reference the second vars or second distribution button. It's where you find normal CDF. And all you have to do is you're going to scroll down. You're going to have to go a little bit of a ways until you actually hit the letter A. So it's the letter A. You scroll down. And what you type in for this, folks, is you choose binomial PDF. The P here, by the way, stands for a point. And we want it for a particular point of exactly 2. And the parameters are this. They ask you for the number of trials, the probability, and what X is. What is the success you're looking for? So we're going to do N is 4, P is 1/6, and X we're looking at in this case is 2. If you type this in, you will get exactly this answer. Okay, let's look at B. Should the player be surprised if he gets doubles more than twice in 4 attempts? Okay, this is a different probability question, just slightly different though. What's the probability he gets doubles more than twice? So what I want to find is the probability that X is greater than 2. Okay, this is a discrete variable, so the answers are either 0, 1, 2, 3, or 4. There's nothing in between. So greater than 2 means not including 2. So really we want to find the probability that X is equal to 3, and we're going to add to it X is equal to 4. Okay, so what we can do is we can actually write this out using the binomial formula like this if we wanted to. It would look like this. Right here, what I would do for the probability of 3, I would do it's 4 choose 3, and I have success for 3 times, failure for once. For this guy here, for probability is 4, I would do 4 choose 4. Success is 4 times, failure is 0. If you add those up, you're going to get 0.016. Okay, now I'm going to show you on the calculator how to do it. In the calculator, we're going to reference again second vars or second distribution. And all you want to do this time is we're going to use the CDF button. And what CDF is, you have to be careful. CDF means cumulative. So this is accumulation is what we want. And here's the deal. On the normal CDF, you could go from any range that you wanted to. But on binomial, it only counts backwards. So if we have a distribution, for example, and it's binomial, maybe it looks like this, the calculator only goes from the point you tell it all the way back. It can never go and get you like this little range in here. It can't do that for binomial. So you have to be thoughtful on it. Well, what it's going to do is I can actually find the binomial CDF. Why don't I do for 4 and 1/6? What did I say from 2 all the way down? So using CDF means cumulative from 2 all the way down. So it's going to find all of the answers for 2, 1, and 0. If I can find the probability that I get 2, 1, or 0, I can take this answer, subtract it from the whole, and it will give me this. So on that one, when I do this answer, and you can try it yourself, you will get that particular case. I do like the calculator on this one, but you have to be really careful on binomial when you find probabilities that aren't equal to, because equal to is easy. That's just binomial PDF, you plug it in. Very straightforward. But when you have something greater than or less than, where it's an accumulation of multiple numbers, you're going to use CDF, and you have to think about it. Remember, it's whatever you type in from here all the way down. It's backwards. It'll never go to the right of a distribution. So you may have to do some clever subtraction. Okay, let's do this again. We are looking at the doubles in 4 attempts with the same parameters. Find the value for the probability distribution. I'm going to show you just where the probabilities came from on this distribution. All that we had to do is realize every cell on this probability distribution is a PDF. It's a point. So to find the answer when x is 0 versus x is 1, I'm literally going to use the calculator, and I'm going to type in binomial PDF of number of trials, the probability, what x am I looking at. When you do that, if you do binomial PDF of 4, 1, 6, and 0, you are going to get that particular answer. Okay? And you can do that for 1 and so forth. Just trust me on this. This is the distribution for this particular binomial scenario. It will change based on the different types of scenarios we're looking at. Now be careful. Remember, for normal CDF, we have to state certain parameters if we use calculator speak. Because I'll tell you, I use this calculator speak all the time for binomial. If you do this, you must state on here, what I would do is say that's n, I would say that's p, and you need to say it's a binomial distribution. Now, it might seem really silly to write the word binomial distribution because it shows it right here. They're not going to take calculator speak. They are not going to assume that they know what that is. You must tell them it's a binomial distribution, and you must state the parameters here that are being used. That is, in this case, you have to identify n and p. I use this Coke example just to show you the required work that you must have on your paper for this. Here's a situation. Given that I'm going to drink 5 different beverages today, what's the probability I drink exactly 1 Coke, given there's a 20% chance I drink a Coke? Okay, so in this case, for stating the type of distribution, what I have to do is say it's a binomial distribution, and I have to show bins somewhere. When you do this, I'm going to say it's binomial, where success is drinking Coke, failure is not. I'm going to show it's independent because having 1 Coke doesn't impact the other decision. The number of fixed trials is 5 times, and I'm going to say the probability of success is always 0.2. So for binomial, you must state that. And I'm covered because I've talked about the distribution, so covering the distribution is done. Next, state the values of interest. So in this case, I want to know the probability that x is equal to exactly 1, and x is the number of times I drink a Coke, so I'm defining the variable. Okay, show my work or use the calculator. If I use the calculator, I'm just going to put binomial PDF. I'm going to put n, p, and 1. I'm going to define n and p. And I even like to define the x there. I just kind of cover my basis. And I've already said it's binomial, so technically I'm okay from up here. When I do that, the probability that I drink exactly 1 Coke during the day, and only 1 Coke, has about a 41% chance that that will happen. Now I do want to make sure that you're cautious on this. Let's say if we're talking about the Coke example, and I want to know what is the probability I have 2 or more Cokes a day. What you want to make sure, so the number of Cokes could be 0, 1, 2, 3, 4, or 5. There's actually 6 outcomes for this. So I like to really write this down and visualize it. Of having 2 or more Cokes a day would be any of these scenarios. Now again, we have to be careful on binomial. When we use the calculator, it's going to actually show us the bottom half. So to be clever with that, what we want to find is the probability that x is less than or equal to 1. So for this here would be binomial CDF, because it's cumulative, of 5 trials, 20%, and I want to know from 1. Now it's cumulative, which means it'll be from 1 all the way to 0, so it will find the total of these 2. Take 1 and subtract this from it, and that will end up giving me these 4 scenarios. This is not the only way to do this problem, by the way, folks. If you wanted to, you could do binomial PDF of this, PDF of this, PDF of this, PDF of that, and add all 4 of those together. You will absolutely get credit for that.